The second part of lesson 6.1 has us modeling exponential functions involving growth and decay models. If you're looking at an exponential growth model, the equation is going to look like our exponential functions from day one. Y equals a times b to the x power. Now when you model equations with these types of functions, you're going to be modeling changes in population, changes in value. The a portion of your equation is going to be the original amount in the word problem. B will represent your base or your growth factor. In order for your function to represent growth, b has to be greater than 1. When reading a word problem, to get the b value, you'll take 100% and add whatever the increase is going to be in your growth function. And that will help you determine your growth factor. Let's take a look at example 2a on the right. The population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% over the next 4 years. What exponential function models the population of the city in that 4-year period? The things that we're looking for are the a and the b values. We don't have to plug in anything for x and y. The a value represents the original amount of the population. That's going to be 4.6 million. That's how many people were there in the year 2010. So we'll say 4.6. To get our b value, we're going to take 100% and we literally add the percent growth rate or the percent rate of change for the increase, which is 1.3%. Easy enough, that's just 101.3%. Now to write our equation, we write y equals a, which was that 4.6, and then to get our percent on the inside, or our growth factor on the inside, we'll take 101.3 and convert it to its decimal counterpart, which would be 1.013. That's your b value. And we'll put that in parentheses just to recognize that we're not going to multiply the 4.6 and the b together. And then we raise that to the x power. That's literally all we do. There's your equation. We can then use this equation to predict a different value. For part B, it says if the population continues to grow at the same rate, so beyond those 4 years, what will the population be in the year 2040? Now we have to think about what the variables stand for, because if we plug in the year 2040, that number won't fit on our calculator. That would be pretty big. Remember up at the beginning, when it talked about the population initially, they started the population in the year 2010. X would then actually represent years since that time. Whoops, 2000. Hang on. Here we go. Let's try that again. 2010. For example, this year, 2020, we wouldn't plug in 2020 to the equation. 2020 would be 10 years after the year 2010. If we want to predict the population in the year 2040, what will we plug in for x? Well, if we take 2040, that would be 30 years from the year 2010. That's what we should plug in for our input. Y would be the population, that's our output. So y would equal 4.6 times 1.013 raised to the 30th power. Now that's going to be big enough. If you type this into your calculator, you should be able to type it in all at once, keeping in mind that you would type in your 4.6, then do the parenthesis 1.013, and use the arrow up key, that little kind of carrot looking key, or the y to the x button and raise it to the 30th power. To the nearest hundredth, we would get approximately 6.78. But that isn't a person, it's not 6.78 people. The label is millions of people. That would be the approximate population with that growth rate. Our next example is going to model exponential decay. A decay model loses value over time or decreases. We're still going to use our exponential growth equation, y equals a times b to the x power. A will stay your original amount or that constant. B is now going to be called the decay factor instead of the growth factor. In order for your function to model a decay, or to be a decay model, the b value needs to be between 0 and 1. To get b, if you know the percent that your function is decreasing, you would take 100% minus the percent decrease. And then you can use it to predict future output values. Over on the right, example 2b. A car was purchased for $24,000. The function 24 times 0.8 to the x can be used to model the value of the car in thousands of dollars, x years after it was purchased. Does this function represent exponential growth or decay? If we look at our function, we have y equals 24 times 0.8 to the x. Notice our factor on the inside is 0.8. So that means it's less than 1. Because of that, this would be a decay model. Pretty easy. That means over time the car will lose value. What is the rate of decay for the function and what does it mean? In the equation, the decay factor is 0.8. Because of that, that would be 80, if you convert that to percentage, that would be 80%. That means each year the car is worth 80% of its original value. To get the actual rate of decay, we have to use our formula backwards. Instead of saying b equals 100 minus the percentage, we already know what b is. B is 80%. And if we take 100 minus the b value for the growth factor, b would equal 20. That means the rate of decay is 20%. Each year, the car loses 20% of its original value. That's a pretty steep loss. Part C. The graph of the function is shown. Take a look at that graph. Can you guys tell where it crosses the y-axis? And then as time progresses, what happens to the value of that car? Hopefully you can tell it looks like it's decreasing pretty rapidly. After a while, the car won't be worth very much money. Okay, so it says, what do the y-intercept and asymptote represent? Well, if we look up here, the y-intercept, it looks like it crosses at 24. That would be the original value, or the start point for the function. So that's the original value of the car in thousands of dollars. Then we're asked about the asymptote. Well, if you look over at the bottom on the right, I think it says 25 way over there in the corner. It's looking like the graph kind of levels out and it's not going to go below the x-axis. So the asymptote would represent a value of $0. And because the car value plateaus, it never goes below, that means it's never going to be worth less than $0. Last but not least, what is the value, or when will the value of the car be about $5,000? Well, the when is the x-axis, so we need to figure out where are we at $5,000. That would mean the y-intercept, or the y-axis, would have to equal about 5, because the y represents the value in thousands of dollars. Looking at the graph, if we go to where the y value is 5, I'm just going to go kind of along that location till we get to the point of intersection. On the x-axis, the value that matches with that point, let's see, it's between 5 and 10. It looks like 7. it looks like it would take 7 years. That's not that long of time for the value of the car to go from $24,000 down to only $5,000. And that's where we'll stop for 6.1 day 2. Your assignment today will be to log into Pearson and complete the 6.1 Pearson assignment. If you have any questions, please let me know.